Hi everyone. In this video, we will be discussing about isomers. So what are isomers? Isomers are set of chemical molecules having identical molecular formula but differing in their chemical and physical properties. So molecular formula will be identical and they are differing in their properties, chemical and physical properties. There are two main types of isomers. One is structural isomer. Another one is stereoisomer. Two main types of isomers, structural isomers and stereoisomers. What are structural isomers? Structural isomers are the isomers having identical molecular formula but differing in their structure and properties. The difference in the structures of the structural isomers are very obvious in their two-dimensional structural standpoints itself. Now let's see what is stereoisomer. Stereoisomers are the isomers having identical molecular formula differing in their structure and properties. Unlike structural isomers, the structural difference of the stereoisomers are not very obvious from their two-dimensional structure itself. The structural difference of the stereoisomers are very obvious from the three-dimensional structural standpoints. Now let us discuss about structural isomers. There are many types of structural isomers. Let's discuss about one by one. The first one is chain isomers. Chain isomers are differing from each other in their carbon chain. For example, consider butane, N-butane, CH3, CH2, CH2, CH3. The name of the molecule is N-butane. Now, let us draw another molecule, CH3, CH, CH3 and CH3. This is 1, 2, 3 propane. The methyl group is the second carbon atom, so 2-methyl propane. N-butane and 2-methyl propane are chain isomers because the two molecules have identical molecular formula C4H10. Here also the molecular formula is C4H10. So identical molecular formula but differing in the carbon chain. So these type of structural isomers can be called as chain isomers. Now let us consider another example for chain isomers. 2-methyl butane. 2-methyl butane. So the structure is CH3, CH2, CH, CH3 and CH3. This is 1, 2, 3, 4. You should give the number such a way to give the least number for the substitution. So number should be 1, 2, 3, 4. So 2-methyl butane. The molecular formula of this compound is C4H12. 1, 2, 3, 4, 5. Actually C5, 3, 5, 8, 9, 12. C5H12, the molecular formula. Now let us see another molecule, CH3, C, CH3, CH3 and CH3. The molecular formula of this compound is also C5H12. So molecular formula are same, but the two molecules are differing in their carbon chain. So these two molecules can be called as chain isomers. So what is the name of this compound? Now you have to see the long chain. 1, 2, 3. So propane. and two methyl groups are attached on the second carbon atom. So it's called 2,2 dimethylpropane. Dimethylpropane. So this is another example for chain isomers. Discuss about another type of structural isomers, position isomers. Position isomers are differing from each other in the position of specific functional groups present in the structure. What are functional groups? Functional groups are the active site of the molecules. There are so many functional groups. Double bond is a functional group. Triple bond is another functional group. CO is keto groups. CHO, aldehyde group. COOH, acidic groups. OH, hydroxyl group. SH, thiol groups. These are the functional groups. So position isomers are the two molecules. They are differing from each other in the position of a specific functional groups in the structure. So let us consider 2-butene. So CH3, CH, double bond, CH, CH3 is a butane. Double bond is there, so butene. The butene is present in the second carbon atom. So the molecule can be named as 2-butene. So the molecular formula is C4H8. Okay. Now the functional group is a double bond. Now let's see another molecule, CH2 double bond, CH single bond, CH2, CH3. So what is the molecular formula of this molecule? C42358 H8. So same molecular formula, differing in the position of a particular functional group. So here the double bond is present in the second carbon atom. Here it is present in the first carbon atom. So this can be called as 1-butene. So the two molecules can be called as position isomers. Okay, so now we have discussed two types of structural isomers, chain isomers and position isomers. Now we will be discussing about functional isomers. Functional isomers. Functional isomers are the two molecules that are differing in the functional group. Example, consider CH3, CH2OH. This is ethanol. Or it can be called as ethyl alcohol. Ethyl alcohol. What is the molecular formula of this molecule? C2H6O. Okay. Now, let's consider another molecule having the same molecular formula, C2H6O. So now here the functional group is OH, hydroxyl group. Now consider this molecule, CH3O, CH3. So what is the molecular formula? C2H6O. So the two molecules have identical molecular formula but differing in the functional group. Here is OH group, here is oxygen. So the two isomers can be called as functional isomers because the two molecules are differing in the functional group. Okay, now let us discuss about metamers. Metamers are the two molecules that are having identical molecular formula but differing in the unequal distributions of carbon chains on either side of the functional group. See, let's have an example, CH3, CH2O, CH2, CH3. This is ether. This is ethyl group, this is another ethyl group. So the name of the molecule is diethyl ether. Ether. Now let's see the isomer of this molecule, CH3O, CH2, CH2, CH3. Now in both cases, the functional group is ether. Ether. In this case, this side there are two carbon atoms and this side another two carbon atoms. But consider this molecule, here 1 carbon atom, here 3 carbon atom. These type of isomers can be called as metamers. So metamers, the number of carbon atoms on either side of the functional group will be different from each other. So now we have discussed about 4 types of structural isomers. So what are they? Chain isomers, position isomers, functional isomers, meta isomers. Now the 5th one is tautomers. Tautomers are very special type of structural isomers. Tautomers are the isomers of your molecules having 2 different chemical forms under dynamic equilibrium. So let us discuss about ethyl acetoacetate, that is CH3, CO, CH2, CO, O, CH2, CH3. The name of the molecule is ethyl acetoacetate. Ethyl acetoacetate. Now, see, now this is called keto form. We have double bond O here. This is keto form. Keto form of ethyl acetoacetate. The molecule will also have another chemical form which is called enol form. Enol form. The enol form structure I am going to write now. CH3, COH, double bond, CH, CO, O, CH2, CH3. The name of the compound is ethyl acetoacetate. Ethyl acetoacetate, ethyl acetoacetate. But this compound is the keto form of this ethyl acetoacetate, and this is enol form of ethyl acetoacetate. These 2 forms are in equilibrium, dynamic equilibrium. This type of isomers can be called as tautomers. Now let us discuss about geometrical isomer. Geometrical isomer is a type of stereoisomers. Okay, stereo isomers. There are 2 types of stereoisomers, as I told you earlier. The first one is geometrical isomers, another one is optical isomers. There are 2 types of stereoisomers. One is geometrical isomers. The another one is optical isomers. Now first discuss about geometrical isomers. The geometrical isomers are cis-trans isomers of a molecule. The cis-trans form generally exists because of restrictions of single bond or double bond in the molecules. Let us consider butene, CH3, CH, double bond, CH, CH3. So this is butene. Now I write another molecule, CH3, CH, double bond, CH, CH3. The same. Now what will say? These 2 are same molecule. Actually not. This is cis butene. This is trans butene. As I told you, the 2 molecules have same molecular formula but differing in the structure. The difference in the structure can be viewed only from the 3-dimensional standpoints. Now I will write about the 3-dimensional structure. So see, CH3, C, double bond, C, CH3, H, H. Just to view, these 2 CH3 on one side, this 2 H on another side. This is above the plane, this is below the plane. So this is called cis. What happens here? C double bond C, CH3, H, H, CH3. This is trans because these 2 CH group on opposite to each other. In this case, they are in the same site. So this is called cis-butene. This is called trans-butene. So this type of isomers can be called as geometrical isomers. Let us discuss one more example. So C double bond C, COOH, COOH, here H, here H. This is called malic acid. This is called malic acid. Now C double bond C, COOH, COOH, H and H. This is fumaric acid. So these are another example. These are another example for the geometrical isomers. Now I draw 1,2-dimethyl cyclopropane. This is propane. What is this? CH2, CH2, CH2. 3 carbons, so propane, cyclopropane. This is cyclopropane molecules. Now I substitute one CH3 over here, CH3, another CH3 over here, CH3. So here is H, here is H. Now I draw another molecule, 1,2-dimethyl cyclopropane. See. H, CH3, here H, CH3. Now in this case, the two methyl groups are above the plane. This cyclopropane, considered it is in the plane. Now the two methyl groups are above the plane, the two hydrogens are below the plane. So in this case, this methyl group is above the plane and this is below the plane. So this is cis, this is trans. This is cis 1,2 dimethyl propane. This is trans 1,2-dimethyl propane. So this is another example of geometrical isomers. Now let us discuss about optical isomers. Optical isomers. Optical isomers are the isomers having identical molecular formula but differing in their optical activities or properties from each other. So now what is optical activity? Optical activity. Optical activity is the capability of a molecule rotating the plane polarized light either on the right side or left side. When you pass a plane polarized light through the compound, if the compound is capable of rotating the plane polarized light either on the right side or left side, then the compounds can be called as optical active compounds. The compound that rotates the plane polarized light on the right side can be called as dextrorotatory. Dextrorotatory compound. The compound that are capable of rotating the plane polarized light on the left side can be called as levorotatory compound. Levorotatory compounds. So the optical isomers are differing from each other in their optical activity. The dextrorotatory compound can be denoted as D, small d, letters. The levorotatory compound can be denoted as L. So the D and the L are optical isomers. So now, to be optical activity, what are the prerequisite parameters? Now we say the optical activity. To be optically active, what are the structural requirements for the compound? To be optically active, the compound should have chiral carbon atom. Chiral carbon atom. Atoms. Okay. Second, the compound should be dissymmetry. Dissymmetry. When the two conditions are fulfilled, the compound can be called as optical active compound. Now let us discuss with an example. Consider lactic acid. Lactic acid. So what is structure of lactic acid? C, COOH, CH3, OH and H. So this is lactic acid structure. So how many carbon atoms in the lactic acid? 3 carbon atoms. 1, 2, 3. So this carbon atom, well, now consider this carbon atom has 3H. So what is chiral carbon atom? Carbon has 4 valency. 4 valency. When all the groups attached to the carbon atom are different from one another, the carbon can be denoted as chiral carbon. The chiral carbon A is not equal to B, is not equal to C, is not equal to D. When all the 4 substitutions are different from one another, the carbon atom can be called as chiral carbon atom. Now in the case of lactic acid, we have 3 carbon atoms, and this carbon atom we have 3H. This carbon atom is H, and the rest of the groups. So this is not a chiral carbon atom. Now what about this carbon atom? This is also not a chiral carbon atom because there are 2 O attached to the same carbon atom. Now look at this carbon atom. Here H, here OH, here COH, here CH3. All the 4 groups are different from one another. So this is chiral carbon atom. So when a molecule has one chiral carbon atom, the molecule can exhibit 2 power n number of optical isomers. Optical isomers. So now here 1 carbon atom, so 2 power 1 is equal to 2. There are 2 optical isomers possible for this lactic acid. So presence of chiral carbon atom is essential but not sufficient. The molecule should also fulfill another criteria, that is dissymmetry. The molecule should not have plane of symmetry. In the sense, the molecule should not be divided into 2 equal halves. Equal halves. Then we can say this molecule lacks plane of symmetry. This lactic acid, as you can see, there is no plane of symmetry. So the 2 conditions are fulfilled. So lactic acid is a optical active compound. Now, so consider the lactic acid. So what is structure of lactic acid? C, COOH, CH3, OH and H. So this is the chiral carbon atom. So only 1 chiral carbon atom, so 2 power 1 is equal to 2. 2 optical isomers are possible. So when you have this molecule, say the mirror image of the molecules. What would be the mirror image? Here C, OH, H, and here COOH, and this is CH3. So the mirror image of this compound is another isomer. Is another isomer of this lactic acid. This can be D and this can be L. In other words, this form may rotate the plane polarized light on the right side. This form may rotate the plane polarized light on the left side. So this is D isomer, D lactic acid. This is L lactic acid. Now the 2 forms, the D and L form of lactic acid can be called as enantiomer. So what is enantiomer? Enantiomer are the mirror images but not superimposable. This molecule and this molecule are mirror images. They are optical active compounds, but they are not superimposable. So mirror images, non-superimposable optical isomers can be called as enantiomer. Now let us consider another example. Three bromo 2 butanol. 3 bromo 2 butanol. So butanol, so 4 carbon atoms. Okay, 3 bromo, 2 butanol, so CH3, H, H and CH3. So this is the structure of 3 bromo, 2 butanol. Now how many carbon atoms in this molecule? 1, 2, 3, 4. 1, 2, 3, 4. So how many chiral carbon atoms? So of course this is not a chiral carbon atom. This is not a chiral carbon atom. Now look at this carbon and this carbon. So now consider the second carbon. So H here, in this position H, in this position OH, here CH3, the rest of this one. So this is chiral carbon atom. Okay, this is chiral carbon atom. What about this one? Here you see H, Br, CH3 and the rest of this. So this is another chiral carbon atom. So there are 2 chiral carbon atoms in this molecule. So how many possible optical isomers? You have to use the mathematical expression 2 power n. So 2 power 2 is equal to 4 optical isomers are possible. 4 optical isomers are possible for this compound. Now what would be the mirror image of this compound? So if you say the mirror image of this compound is CH3, C, OH, H, C, H, Br and CH3. So one of them is D form and the other one will be L form. So these two are enantiomer because they are mirror images, not superimposable. These two forms can be called as enantiomer. Now think about another form of this molecule. So CH3, C, OH, H, C, Br, H, this is Br, H and CH3. The mirror image of this chemical form is CH3, C, OH, H, Br, C, H, CH3. So these are mirror images. So these two, one of them will be D, another one will be L. Upon doing the experiment only, we will make sure which is the exorotatory, which is levorotatory. By looking at the structure, we cannot predict the optical active property of the compounds. Now these two isomers are enantiomer because they are mirror images, not superimposable. So this is one enantiomer, this is another enantiomer of this compound, 3 bromo 2 butanol. Now what about this compound and this compound? These two compounds, for example this and this, okay, these two compounds are not mirror images, also not superimposable. These two compounds can be called as diastereomers. Diastereomers. Similarly, this compound and this compound can be called as diastereomers because they are not mirror images, they are also not superimposable. These two compounds can be called as diastereomers. Now, look at these two compounds, enantiomer. This is enantiomer, D and L. When this mixer, when you consider these two compounds are the mixer. The mixer we have 50% of D and 50% of L. Then the resultant mixer can be called as racemic mixer. Racemic mixer. So racemic mixer is the equal amount of D and L form. So the racemic mixer is optical inactive because the effect of D will be neutralized by the effect of L. So racemic mixer is optical inactive. So now what we discussed, optical isomers. To be optical active, the molecule should fulfill the 2 criteria. One is the molecule should have chiral carbon atom, one or more than one chiral carbon atoms. Second, the molecule should have dissymmetry, or in other words, should not have plane of symmetry. When the conditions are fulfilled, the molecule can be optical active. Depending upon the number of chiral carbon atom, number of optical isomers are possible. Now we discussed about 2 types of molecules, lactic acid and 3 bromo 2 butanol. I will explain one more example under this category. We will discuss about tartaric acid. It's a very interesting molecule. Tartaric acid. Tartaric acid structure is COOH, C, C, COOH, OH and OH, H and H. This is tartaric acid structure. There are 4 carbon atoms. So this is not a chiral carbon atom, this is not a chiral carbon atom, this is chiral carbon atom, this is chiral carbon atom. So this molecule has 2 chiral carbon atoms, so we expect 2 power n 4 optical isomers for this molecule. Now let's draw the first mirror image for this compound. The mirror image for this compound is COOH, C, right, OH and H, CH, OH, oh sorry, here is H, here is OH and COOH. So these are mirror images. One of them will be D, another one will be L. So these two are enantiomer and these two are optical isomers. Now look at the another optical isomer of this compound, COOH, C, COOH, OH, OH, H and H. Something interesting? See here we have 2 chiral carbon atom, of course, but this form of the tartaric acid, this is tartaric acid. This form of the tartaric acid has plane of symmetry. You can divide these 2 molecules into 2 equal halves. So because of this form is optically inactive. Though the tartaric acid has 2 chiral carbon atoms, we will not have 4 optical isomers of this compound because one of the form has plane of symmetry. Because of the plane of symmetry, this compound will not exhibit optical activity. This type of compound can be called as meso compound. So meso compound will not have the optical activity. You should not confuse with the racemic mixer. Racemic mixer is the equal amount of D plus L. That is racemic mixer. The racemic mixer, D is optical active, L is optical active. But since we have equal amount of D and L, the racemic mixer is optically inactive. But meso compound is optically inactive because of the presence of plane of symmetry. So these are the things about the isomers. I hope you understood the various isomers of the chemical molecules. Thank you so much.